Thanks a lot for the possibility to talk here, for the invitation. So the work I want to present here about non-collision singularities is part of my doctoral thesis. Oh, okay. This work on non-collision singularities is part of my doctoral thesis under the supervision of Andreas Knauf in Erlangen. Yeah, and I will start with a short historical repetition of what non-collision singularities are, because I am not quite sure if everybody is familiar with that. And afterwards, I will talk about the so-called 4+4 system, which is one example where one can prove the improbability of non-collision singularities that I was investigating in my thesis, or am investigating. Okay, so first of all, the repetition on the n-body problem. We describe it in a Hamiltonian formulation. So we have a Hamilton function h that depends on the momenta p and the positions q, and it splits into a kinetic part and a potential. The kinetic energy is as usual, but the potential is not necessarily the classical one from celestial mechanics. So we allow interaction constants Zij that depend on the pairs of particles we are considering, and we have here an exponent alpha that can be any number between 0 and 2. Yeah, this is slightly more general. The case of celestial mechanics would be that alpha is equal to 1, and the interaction constants are minus the product of the masses of the particles. Okay, and this equation is not defined everywhere, so we see there's a problem if the position of two particles in RD coincide. So we have to restrict the phase space. So the position space is restricted such that this never happens. And then we usually assume to be in the center of mass frame as well, because the motion of the center of mass is, so the total momentum is a conserved quantity, and so this is just a straight line motion, and we can reduce it to have the center of mass fixed in the origin. This is the second condition. Yeah, and as probably everybody knows, and we have a Hamilton function. We consider it on a cotangent space that has a symplectic form. So we have Hamilton's equation, and in coordinates, please read in the usual form that the change of the positions is just the momenta divided by the masses, and the change of the momenta comes from the potentials of the other particles. Okay, and this vector field we have generates a flow, and this flow exists locally, but the question is whether it exists globally as well. And we can always say it exists on a maximal interval of time between some escape times, t minus and t plus, depending on the initial condition. And what we are interested in are those initial conditions where the escape time t plus is finite. So we have a singularity. The solution only exists up to a finite time, and we will denote with thing the set of all those singularities. And of course, it is clear that in the n-body problem there are singularities. The simplest one are the collision singularities. You have two particles, and they are moving up to each other, then they will reach a point that is not in the phase space, because the positions will coincide. And yeah, so we have a singularity. And the question is now, are those collision singularities the only singularities? The binary collisions can be regularized, as probably all of you know. So these are no problems. One could extend the differential equations afterwards. But at least if you get three-body collisions, then you have a problem, because there is no general method to regularize them any longer. So one question is, are all singularities due to collisions? And the second will be, is the set of initial conditions leading to singularities a set of measure 0? But, So I will start now with an historical overview on this topic. And one of the first who investigated the question of singularities in the n-body problem was Paul Lévy in his lectures given in the year 1895. And yeah, this was a large set of lectures he gave on celestial mechanics, and in the end, he came to the problem of singularities of the n-body problem, and he derived a condition for singularities. Namely, if you have a singularity, then in the limit to the escape time, the minimal distance between two particles has to converge to zero. So this is rather obvious because you need some source of energy. You have these two parts, the kinetic energy and the potential energy. And if you want the kinetic energy to diverge, you need to have large negative amount of potential energy. And this can only happen if two particles are very close to each other. And yeah, so this condition could be established. But this does not mean that the singularity is due to a collision, because it's the minimal between any two distances. And a collision, I will define it soon, is a singularity where all particles have a definite limit, and the limit to the escape time. So, yeah. And then some further investigations were made really early by von Zeipel in the year 1908. And as there was some doubts about this proof, got another version by Sperling in the year 1970. And they could prove some interesting properties of singular orbits. First of all, they investigated the moment of inertia, which I will denote with a J. It is just defined as the sum of the squares of the positions weighted with the masses divided by 2 for convenience. And yeah, they could prove that this quantity always has a limit if we have a singular orbit. But this limit could be plus infinity as well. And yeah, so, and the second part is, we can define now collision singularities where this limit exists, and the existence of the limit of the positions is equivalent to the moment of the inertia having a finite limit. And of course, now we can, as this limit always exists, we can split the set of singularities in one set of collision singularities, where the moment of inertia is finite, the limit, and the set of non-collision singularities where this limit becomes infinite. Yeah. But the question was, do such non-collision singularities exist at all? Because we can split anything. If one part is the empty set, then there is nothing interesting. And before I will say something on that, first, then the set of collision singularities is well understood in the sense that one could prove that this set is a set of measure 0. There were some results by Sari and another result I will come to later. So if one wants to prove the improbability of all singularities, the non-collision singularities are the one has to focus on. Okay, but first of all, we will ask ourselves about existence. And there, the first old result was given by Paul Lévy himself, who could prove that the set of non-collision orbits is empty if we have 3 or less particles. But he already conjectured that there could be non-collision singularities if we have 4 or more particles. And why the set of non-collision singularities in the case of 3 particles is empty, one can sketch, and it is in some sense in the similar to the talk we had in the morning today. So first of all, we need 2 particles that are very close together, because we have this condition of Paul Lévy that the minimal distance between particles needs to go to 0. So there is some cluster of particles that are very close together. And now we can consider the motion of the center of mass of this cluster. So we consider it as one cluster. And as long as the third particle is far away, this cannot get accelerated any longer. So in finite time, it cannot reach infinite space and position. So in order to have an acceleration, we need a third particle that comes close to these 2. In some sense. And then something interesting happens because we have a 3-body motion and it's complicated to describe it. Yeah, but as long as these three particles are close together, their center of mass cannot get accelerated any longer. Because, so if we are in the center of mass frame, we are close to the origin, because all the particles are close to each other. So at some later time, this third particle has to move away again. This can lead to this cluster moves in the opposite direction. Yeah. And now we are in the same situation as in the beginning. The two particles cannot get accelerated any longer, because the third particle is moving away from them, and the third particle cannot get accelerated as well, or it has no reason to come back. It could, probably, but it would take a lot of time, and we want collision, so we want singularities. We can always assume we are close to the escape time, and then there is not enough time for this particle to come back. Yeah. And so there needs to be something that leads to any of these clusters to come back. And this could be a fourth particle. If this were here, then these particles could interact again with each other. It could lead to that one of them is turning around, reaches again the binary cluster, and then we could have a non-collision singularity. So this was the idea of Paul Levé already. And it took a lot of time, almost 100 years, until such an orbit could really be constructed by Schier. Yeah. But he used 5 particles in dimension d equal to 3. And the construction of Schier is similar to what I have sketched already. So he had a binary cluster moving on. I'm not good at drawing, but they were moving similar on elliptic orbits in a plane. And then a messenger particle was moving on an axis perpendicular to the plane to reach this binary cluster. And then it is important to have the right timing. This was based on some work of Maser and McGehee, who investigated such orbits, that this is possible, that this particle arrives just at the right timing, where this binary cluster is at a close approach of the particles, and then it can happen that this particle moves here and gets kicked up again. This leads to the fact that the binary cluster, so this plane, is moving downwards again. Yeah, now we would have the same problem as before. These particles do not come back, but we have 2 particles left. So if there is a second binary somewhere here, yeah, we can have again the right timing, and Schier proved that this construction worked. You can get an infinite amount of such passages, and the time between those is always getting shorter and shorter, and the acceleration leads to the system to diverge to infinity. So he constructed a non-collision singularity this way. Okay. And yeah, there were some other constructions as well. One of them was done by Gerber, who used a large number of particles on some sort of regular polygon. And more recently, the work by Schuhe, which he put a preprint in the year 2014, but it got published in the year 2020, who solved the problem completely of existence, because he could reduce the number of particles to 4 and the dimension to 2, which are both hard obstacles to overcome, because the third dimension in Schier's example was necessary so that you don't have collisions before the non-collision singularity, so the particles don't meet each other too early. But Schuhe did all of this, and so the existence problem is done in some sense. Okay, all of these constructions need some special masses. Also there are put some conditions on the masses that the clusters have equal mass or something. This is still necessary, but there are non-collision singular orbits in all of these cases. Yeah, and parallel to this development, there was a second question that I already posed, namely the question of improbability of non-collision singularities. So is the set of initial conditions leading to a non-collision singularity a set of measure 0 or not? And the first result was already given before. The first example of a non-collision orbit was constructed by Sari in the year 1977. And he could prove that non-collision singularities are improbable in the case of n equal to 4 particles in dimension d larger or equal to 2. And all exponents alpha between 0 and 10 divided by 7. Yeah. This was a first result. And then this was improved by Fleischer, who was a former doctoral student of my supervisor as well. And he developed in his thesis the so-called Poincaré surface method, which is a tool to prove improbability of certain sets of initial conditions or orbits. And he could use this technique to prove the improbability of all non-collision singularities with 4 particles in dimension d greater or equal to 2, and all exponents alpha between 0 and 2. So, of course, 0 is a natural lower bound, and 2 is a best possible upper bound, because if you have a potential which attracts stronger than 2, then even collisions become possible or probable, as then the attraction of the particles is too strong. Okay, and up to now, there are no better results known. So it is really hard to get a result for more than 5 particles, because you have way more freedom now. As I sketched in the example with 4 particles, you always have this binary, some outer particle which it might read, and afterwards it had to reach another particle. But now if you have, and well, you can control this motion very good. It is close to a straight line, and I will sketch how close it is to a straight line soon as after I have introduced this method to prove improbability of the orbits. But if you have a 5th particle, then you don't know. If this is maybe here, then it could go there again as well. It is not clear what the system does. There are lots of more possibilities, and you lose some sort of the control of the motion. Okay, but why do we need control of this motion at all? So I will sketch now the so-called Poincaré surface method, which was published in a paper by Fleischer and Knauf after his thesis, because they generalized it a little bit more. Yeah, and what is the general setting there? So we have a smooth manifold, P. You can think of the phase space we had for the n-body problem. This manifold has a volume form. Okay, the pointer doesn't work. This volume form is omega, and we need a vector field. Think of the Hamiltonian vector field we had before, that preserves the volume form. So the Lie derivative in direction of x of the volume form is 0. Okay, and then one wants to find some condition to have improbability. First of all, again, we have a flow if you have a vector field. The flow has a maximal domain, and this escape times t minus and t plus. So, and to get improbability, we need to be in some special sets of the flow. The first thing we want to be is we want to consider points that are wandering. Probably this notion is familiar with most of you working in dynamical systems. Here we have not a complete flow, so it is adapted to this situation. And the point is wandering if it has a neighborhood that is eventually left by the flow after some time, t minus between 0 and the escape time. And then, yeah, it is left, so the intersection of this with the image of the flow is empty. But wandering points are interesting, but they are not improbable. There are many examples of orbits where we have lots of wandering points, or even every point could be wandering. Yeah, this alone does not guarantee improbability. And though we need a second ingredient, and this is where the name Poincaré surface method comes from, we need some sequence of Poincaré surfaces. These are just codimension 1 closed submanifolds with 2 conditions. As usual, they should be transversal to the flow. And first of all, this is necessary to get a Poincaré map, which leads you from one surface to the next. And as a second part is that if we have a transversal, if it is transversal, so we can get a volume form if we insert the vector field X into the volume form omega. So we need one dimension less and insert one vector field. And this can be restricted to the surface. And then we ask ourselves, is the volume of the surface with respect to this volume form finite? And it does not only need to be finite, it needs to be decreasing to 0. So the volume of these Poincaré surfaces has to become smaller and smaller. Okay, it's an oriented volume, but we assume it is positive. Okay, and if we have such a sequence of surfaces, we can talk about transition points. These are points that hit almost all of the surfaces. So the forward orbit, O plus of X, should intersect any of these hypersurfaces after some initial index M0. Yeah, but transition points of such a sequence of Poincaré surfaces are not improbable alone. There are examples as well where one can find out that this is not necessarily a set of measure 0. But if we combine both of these, so we take points that are wandering and transition points to this sequence of Poincaré surfaces, then with respect to the volume form omega, we have the volume of this initial conditions and the orbits, because these are just conditions of the orbit, is 0. So this is a possibility to prove some improbability results. And in the case of singularities, we have one advantage, because singularities are always wandering. Because to be a singularity, in some sense, you have to leave the manifold. And yeah, so you will not re-enter the neighborhood you are from. And by some continuity arguments, you can even lift this to the total neighborhood. So being wandering is not the restriction if you want to prove improbability of a sequence of a set of singularities. So the important thing, still doesn't work. The important thing is to find a sequence of Poincaré surfaces such that we have transition points. Such that the singularities you are considering are transition points to the set of Poincaré surfaces. Okay. And yeah, now I will show you how this can be done in the case of 4 particles in arbitrary dimensions. And this was done, this is the result of Fleischer mainly I will sketch now. And then, as this is the main part of the example I am considering, it is interesting to understand what is happening here. So, yeah, I've already sketched it before. We have this binary cluster, and there's a third particle and a fourth particle, and we can assume that they are moving outwards. Okay, it is not important whether the binary is the cluster that is moving between these outer clusters. It could be a single cluster as well, and this could even change during passages. But usually we have this situation, this binary is approaching. then there is some complicated interaction of three bodies, but afterwards, first of all, they are really close, but we can already see that they are moving in this direction. I should draw a large arrow because they are really, really fast. At these quasi-triple collisions, the speed of the system is gained. And yeah, then we come to a time where this distance is of so here the distance is really close. I could write the scaling if you're interested, but there still large forces are acting. And yeah, this is not good because large forces could perturb the motion really much. So we want to look at a time where the distance is of constant size, say size 1. This happens shortly afterwards. And then, yeah, somehow the binary will move here. Yeah, and then we have the same game again here. And we have this interaction and get the next orbit. So, and at this time where we have a scale of constant size, say 1, there we can ask ourselves, how much does this motion deviate from the straight line that I can, yeah, probably it's not.
Sorry, can I ask?
Yeah.
I'm sure it's my fault for failing to pay attention properly. I'm not getting this diagram at all. The 2 dots in a circle.
Yeah. So this is a binary cluster. I want just to show that they are grouped very close together.
And the arrow is that they are staying together and moving.
Yeah, the arrow is the motion of the center of mass of this binary cluster.
And
because
the 3 lines are the 3 cases.
Yeah, that's a progress in time. And this here should be a splitting line because blue was the wrong color. Yeah, this is a progress in time of this orbit in some sense. And
so this is a splitting line in terms of the system or in terms of the
in terms of the diagram, I hadn't enough space below. And there's another reason for the splitting as well, because here you usually consider the motion of these 2 clusters, whereas on the other side you switch your focus to the next collision where you want to consider the distance between the binary and the other outer cluster, outer particle. Okay. So this is a progress in time. These are, if I could show you a movie, but it's difficult to obtain such orbits because we believe they are improbable. Then you would see, if I stopped at 5 suitable occasions, you could see these pictures in the movie, in the course of the orbit. So, and now the important time is the time where we have constant distance, say 1, between these 2 clusters. And now we can ask ourselves, how close is this motion to the straight line that is given just by the position of the third particle? Because this should be some really stable thing. It is far apart, and one can show that the momentum of this particle is very close. Now we can ask us, I said the momentum is very close. This is just a bound on the angular momentum of this particle's motion. And I will show you the results on the next slide. There's a bunch of inequalities one can derive. And probably I should draw the picture here again, but so we have this binary. straight line here. So first of all, the first condition is to fix the time. At the time we're considering the distance between these two clusters. So this is just the distance of the center of mass of these particles, should be exactly 1. This gives us a hypersurface because it is a restriction in position space. And yeah, the distance, the norm of the third particle should be very large. So it is easy to assume that this is larger than 1. And then we can ask, how far are these particles away from the blue line I sketched? And this, there can be given an explicit bound in terms of the total angular momentum, L, the norm of this, divided by the momentum variables. So, and the momenta diverge, otherwise we would not have enough speed to become infinitely large. So this is really a close scaling to the line. Then the second condition is technical for proving the finiteness of the volume. It says essentially that the particle or the third cluster cannot come. So the positions are always smaller than the momenta, because the momenta, you need a short amount of time to travel one of these, from one cluster to the other. And so the positions must be smaller than the momenta. And yeah, then we have this binary cluster, and this binary cluster provides the energy of the system. So, the potential energy, and the kinetic energy is, together with the potential energy, shall be roughly of the same size, with an opposite sign, of course. And this says, yeah, we know kinetic energy is the momenta squared, and the potential is roughly the distance of these particles to the power of minus alpha. So this says that just that we can estimate the momenta with the smallest distance between any particles. This is done for all momenta you see here. It's always the same argument. And then we can ask how. So first of all, this fourth line could be interesting. How much are the momenta deviating from the straight line? So is this line moving? And there we have an angular momenta bound, and we can say the orthogonal component of this momentum is smaller than a constant times the total angular momentum divided by the distance. And as the diameter of the system is diverging too, this is again very small. And similar reasoning can be applied for the internal momentum. So if I write this internal, it's the motion between the clusters. If you're not familiar with cluster coordinates, you can think of the sum of, it's the difference between the momenta of these particles, and then there are some mass vectors. Okay, and the sixth point is that the energy is always between some bounds minus E and D. Of course, we are in a Hamiltonian system where the energy is always preserved. So this restriction could be dropped, and we could think of non-collision singularities in an energy shell, just restrict the manifold to a given value of the energy. This was done for the four-body system, but so it's even a stronger statement to prove that in every energy level you have improbability of these orbits. Yeah, but as I will generalize it soon, it's better to think of, we consider all non-collision singularities with an energy between minus E and D. And if we can prove that these are improbable for arbitrary values of E, then all of them are improbable. Okay, so this was a really long repetition of things other people did, but it is the main part of the work I've been doing, namely investigating the so-called 4+4 system. So I told you that 5 particles are difficult. If we have more, then we have more possibilities, and we don't quite know all of these possibilities, how such orbits could look like. And so what we do is we restrict our attention to some orbits where we demand from the outside that something is happening. Namely, that the particles split into subgroups that do not come close to each other. And I should draw a picture here. So here we have one system that is diverging in the way I told you. Now we have another system that is doing the same motion, but say the orthogonal direction. It need not be orthogonal, but okay. And from the outset, we assume that particles of these different systems never come closer than some fixed bound delta that is strictly larger than 0. So we always can bound the forces between the systems, because the forces can only become unbounded if the particles come very close. Yeah. And now the question is, are such orbits leading to singularities at the same time of both systems, are they improbable? And if I go back one slide, this is the idea here, how we can prove this. But there are some quantities, namely the total angular momentum and the energy, that are conserved quantity for four-body system. And this is one of the big problems we now have. These quantities are no longer conserved in the 8-body system if we define them accordingly. So it would be natural to consider consider this as the energy of the first system and, of course, an according expression for the second system. But this is no longer preserved. And the bounds we derived earlier, especially the energy bound, is necessary. And the bound on the angular momentum we can see here as well. That this is important. And this is one of the problems one has to overcome. These are no longer conserved. But the question is now, can we control how much they can change during one of these passages? And the second question one should pose is, I said that these four groups are separated, and I say something like both of them diverge. So the moment of inertia for both of them do diverge. But do they have to have this motion I already described? Because Paul Levé's theorem said the minimal distance for a singularity. Yeah.
I lost the dimension here is.
A dimension is arbitrarily larger or equal to 2 of the particles. Dimension 1, there have to be collisions. So.
But I mean, seems to me that the idea is that since you have these two groups and you are able to spread them apart enough in order not to have bad interaction between them, so each of the two can have the required dynamics. So could you figure out that maybe you could have enough space to place 3 groups, 4 groups?
This is not the main problem, to have more groups, but it is difficult because if I show you this equation here, these are really small, so they scale like 1 over the diameter of the system. If we have constant forces, they could perturb this, because we might get some increase of constant size. So we have to make sure that this is really a small impact. And if we know how to make a small impact of, so if any system has a small impact on one of the other, that is of this size, then we could take arbitrarily many. This would not be the problem. But 4 plus 4 is just one toy example to prove whether these concepts work and which restrictions one has to make in order to have this small impact of one system on the other. And the same behavior that we have always particles moving between some outer particles or something all of this is a priori not clear because Paul-Lévesque's theorem only said, okay, the minimal distance between any two particles of this 8 particles has to converge to 0, but this could be only in one system. So it could be that one system provides the total energy for both, if we cannot control how much the energy changes between the systems. So it is only, a priori, it is only necessary to have one cluster that provides the potential energy. Yeah. And then the question on the changes of energy and angular momenta arises, and this, and to apply this improbability result, we need Poincaré surfaces. So the Poincaré surfaces, I can describe it at one time of the system. Say, if the clusters are a distance 1 apart. But I don't know what the other system is doing at this moment of time, in some sense. So I need a bound for the second system during his whole orbit, or as it is having such passages, I need to have a bound where the system is at any time of this orbit. Yeah, this is a little bit more difficult. And yeah, we can formulate it now as a theorem that all of these problems can be overcome in some sense. First of all, we need some restrictions. And one crucial thing is it is easier with this celestial mechanics case of interaction that depends on the product of the masses. And the second thing is that we need, as I draw the orbits perpendicular, this is the best case we can have, because then the time where the systems interact is really short. But if it would be, that the line of the second system would be here, parallel, then the forces could act over a long time. And this could really disturb the motion close to the straight line. Yeah. So we need some assumption that this is not the case. That these orbits are, not parallel. And then one thing is, first of all, these systems behave like diverging 4-particle systems. Namely, they both have an internal cluster that provides the energy of the system. And we have this oscillating motion of the messenger between the outer clusters. And the main thing we have to consider now is the force acting between the system. So we want to bound the integral over the absolute value of these forces. And this is in some sense sufficiently small. It is like 1 over the momentum at the passage. So all of these estimates are first made for one passage, and then you have to sum them up over many passages to see if the bounds are still good enough. And for this is a bit of a problem for the energy. For the angular momentum, we have a good situation. And we can say the change of the angular momenta is really small. It is small in the size times the smaller than a constant times the time for such a passage. And as these times sum up to a finite value, so we have a singularity, the total change of the angular momentum is not a problem at all. And for the energy, this is not the case. If you write it up, the change of the energy is something like the force acting times the momenta. The force is of the size 1 over the norm of the momenta. So the change of the energy is something of a constant size. So at every passage of one system, its energy can increase or decrease by a constant amount. And this is some sort of a problem, because in these estimates we used some fixed bounds on the energy, but it's not that bad because it's only a constant increase, and one can overcome this as most of the system quantities like the kinetic energy or the diameter, they are exponentially lower bounded. So we can take a log of this exponential thing and write it in our Poincare surface, and this will still guarantee us that we have a set of finite volume. And as the last thing I should say is how such Poincare surfaces will look like. And I already said it. For the first system, we can take the usual sequence of Poincare surfaces. This is control the motion at this time where two classes are separating in their distance one apart. But for the second system, we had to find a set of finite volume within which it will always stay close to the escape time. And this, then we have a product, and one can see that the measure of the set essentially is the product of the single measures. And so as the first one goes to 0 and the second is finite, we have no problems. And yeah. So this is one improbability result on non-collision orbits with more than 4 particles. And the idea is, of course, that we hope to use it to tackle other systems as well. But the essential thing is still that we have this divergence of a 4-particle system that is really close to a straight line. And this comes up in all of these analyses. And now my time is up, and I thank you for your attention.